Good evening. Welcome to Quadcast episode 32. In this live episode, I'll be designing a mallet putter, and with the intent that it could be CNC machined. And I'll talk a bit about the features that I add in order to make that easier to do, and how to cope with the tolerance of machines in the design of a product like this, or at least as I would do it with my current level of skill. I'm not claiming to be an expert on this. This is a show and tell of how I would do it, not a expert masterclass on how one should do it, to be very clear. If you're watching this live, then please enter the comments section and also the live chat and send messages if anything needs further explanation. I will attempt to provide that. If you're familiar with this podcast series, you'll know that there's usually the intro music and logo. I haven't worked out the technology for how to play that into this live stream, so whether it's good news or bad news, I'm going to play the sort of extended version of the intro music on a guitar live for you now. And with that, let's get into SolidWorks. So SolidWorks doesn't start up this quickly. It's just because I already had it open and set up to prepare for this live stream. And I'm not going to show you how you normally start it. It's a little bit weird. Anyway, the way I like to start designing, so the putter head I want to design is going to be a mallet style. It will be a zero torque mallet, which means I need the shaft of the putter to go through the center of mass of the putter head. And the issue with that is, trying to do that, the challenge with that potentially is that when you want to so SolidWorks will tell me where the center of mass is and show a point on the screen to mark that, but I can't link geometry to that point, because as soon as you add geometry to the object, that center of mass will move around. So instead, what I'm going to do is say that my objective will be to keep the center of mass of the putter head on this origin point, so I can then line up the putter shaft to go through that that point there. So the way I'm going to do that is take the front plane, create a sketch on it. We'll take a construction line. We'll draw a horizontal infinite construction line. Boom. There we go. We'll draw a as sketched infinite construction line. We'll dimension those with the lie angle of the putter that we want. So most of my putters seem to be set between 68 and 73 degrees. I'm going to set this one at an arbitrary 71. if I was making this for a real market, I would probably make it adjustable, and I'll actually show you a way you can do that. So let me just type in. Yeah, so what I've just done there is we've made a changeable property for what the lie angle is of 71 degrees, because and if later on I'll show you if I needed to change it to 68 or 70 or 72, what that does to the rest of the design. But for now we'll leave it at 71 degrees. And exit that sketch. I will back to the features tab, create an axis on that line. Cool. And we will call that that'll be the where the putter shaft goes in. Now that one, there we go. Don't really need to see that anymore. Let us, though, you know what, never mind. Let's go to the top plane and make a sketch there. So we know we want the center of the putter to be there. Let's get some construction lines in. So that's kind of the left-right midpoint line of our putter. Let's put a normal. So I'm going to use a relatively common trick that we use in this kind of design. I'm only going to draw one half of the putter, and then I will mirror the whole part left to right, thus ensuring that whatever I've done, much later in the process we'll do the mirroring. So whatever I decide to do to make the geometry of the half I actually draw look great, the thing will be symmetrical. So at least the left-right center of mass necessarily will be in that mirrored center line, and then all we have to do is worry about the vertical center of mass and the front to back center of mass. So let's draw a line for a sort of notional putter face, and then we're going to have some kind of tapering tailpiece, because this is what mallet putters normally look like. And then I'll stop drawing straight lines there, and we'll have a curved line for that piece. Let's end it there. So now we need to start dimensioning some stuff. Let us say 8mm, and then the line there. We thought this through enough just yet. So I need to make sure I've got some kind of geometry around this center point, because I need to attach the shaft of the putter to there. And so obviously this dimension from that center line to the putt face is going to be half the depth of the putter. So 30 millimeters is actually probably, that's going to make it in the sort of, that would mean that the putter front to back should be about 60 millimeters. It might be a little bit more if we decide to make the tail longer, or it might be a bit shorter if we decide to make the tail denser but less far to the back. But let's say 30 millimeters is a pretty good distance from the shaft to the center of the putter, to the putter face. Now, let's think about what shape we want for the back side of this. So I know that I want to maximize the moment of inertia of the sort of front part of the putter, and I also need to keep within the rules. And I think actually an efficient way to do that might be to have I'm going to aim to have the putter be less efficient in the center and more efficient as you move slightly further away. So I think for that I need some kind of curve in this shape behind the face, and then to transition that into perhaps a completely different shape up here. So let's at this point in the process, it's probably better if I just draw something without particular regard to whether it's the absolute best thing I could do for what I'm trying to design, and then we can get on to looking at whether it's going to be within the rules. So Vitali asks, am I going to produce a real item from my design at the end? In this case, probably not, because I'm going to design this part so that it could be CNC milled, and I don't have access to a CNC mill. It's also going to be a mallet putter, which is a style of putter I don't personally particularly like. The reason I'm choosing that is because I've spent the last 6 weeks or so designing variations on 3D printable blade putters, and I wanted to give myself a bit of a challenge in this live stream rather than risk regurgitating something I already did a couple of weeks ago. But it does mean that I'm not the customer for this actual putter design. Right, let's take that back to there, and then okay. So once that's filled in, you see it shaded it, so show me that the that's a complete enclosed surface. If I now dimension these things, you'll see it says underdefined down here at the moment. I want to get that to say fully defined, and at this stage of design it's pretty much arbitrary what I'm putting in here. It's just numbers that I think will look okay. And if I dimension you to say 20, now we have fully defined, which is what we want in our sketches. So I will take that and loft it. No, not loft it, sorry. Extrude it. And we will go 12 millimeters up and 12 millimeters down, because why not? Okay. Now, for general safety and usability of putter, well, for safety reasons, you don't want to have sharp edges on things. They also don't survive shipping. So although you can mill something to this shape, it would hurt you if you tried to use it. It would damage the other clubs in your bag, and yeah, and it would not survive in this form. So we're going to either chamfer or fillet all of these corners, but we also have to do something specifically on the bottom of the putter, because a flat surface there will catch on the grass a lot, and it will really annoy the user. I built a putter with a flat bottom in order to understand why no putters have flat bottoms, and it's totally terrible. And my personal opinion on that is that the more, there's a limit probably, but the more rounded the better. And for me, most modern mallet putters are not as rounded as I would like them to be. So this is going to be perhaps a little bit extreme. Let me just save because it's a while since I did that. So we'll take the front plane this time, and actually no, right plane, and we'll sketch there. Thanks. This is because I've got that really long axis that I need to sort out. Let's see where we are. All right. Hide that axis. I think that will. So get a reference. Okay. So what I'm going to say is I want a center point arc from here. Oh no. 3-point arc. There we go. 1, 2. So now dimension that. We're underdefined. Why are we underdefined? We're underdefined because we say that point is on. No, okay, and if I take quite a long way. It's not darling that we are. Oh no, it has. Sorry, got myself a little bit confused as to what I'm looking at. Yeah, okay. So now cut off the bottom of this in a fairly smooth circular way. what I'm going to do now is I am going to do that mirror, but not permanently. So show you what I mean. Yeah. Feature. Okay, fine. So this is now very crudely what the part ahead might look like. We need to make a couple of decisions. So what are we going to have it made out of? And I'm going to say, because I want it to be cheaper to cheapish to make, that 6061 menu will do. So, and now we can go and ask in evaluate what the mass properties are. So it weighs 278 grams, which is about right overall for a putter head. Could be heavier. And we have a problem that we are not in the same maths system as the rules of golf. So this is the rules limit number that matters, I believe. Actually, have I got that right? I think it might be LZZ that matters. That's the one that's constrained. We need to keep this below 5,900, but we want it to be as close to 5,900 as possible. So obviously at the moment we are too low for our standards. So let's start taking some weight out of this putter. But first, I will roll back that mirror. So spline from to spline. Yes, I do, but maybe not yet. So what I'm going to try and design here is a biggish weight at the back. I'm pointing at the screen as if you can see it. A biggish weight at the back that's acoustically largely decoupled from the front part, and then this will be acoustically coupled together to create a wing weight out here that is acoustically coupled to the club face. And I'm going to keep the shaft disconnected from the to some extent acoustically disconnected from the part of the club face that I am trying to keep the weight up for. So let's draw we'll use a spline to try and lay out this kind of counterweight shape that I'm thinking of. Yeah, we'll take that, and then we'll have another spline. Other spline to lay out this shape that I'm thinking of approximately. So, yeah, that's not gone entirely how I want. Let me just drag that around it. what I'm about to ask for. I'm just going to turn off this object now. Right. Let's start mentioning some stuff. It's picked up a midpoint dimension. I don't need that. There we go. Lost the control handles, and that's mildly confusing me. Doesn't really matter. At least I can do this without them. Can we view because we've lost? Fine. Missed a couple of lines I meant to put in, which are here. Shape we can use. Um, to make it a bit easier to machine, I don't want to. I could use offset from surface, but I don't particularly want to do that. I want to make it flat at the bottom, and obviously not extend through the bottom of the putter. Let's say 18 millimeters is a reasonable guess at a number there. And so if we now roll to end, we've got a very weird looking thing, which is appropriate for a mallet putter. They are all generally weird looking. And let's see what our mass properties are looking like. Well, we've decreased our moment of inertia, which is not what I was aiming for, or at least that one. And I do want to show you actually what the effect of different materials is. So if I change this from aluminium to foam stainless steel, let's say, and then we go look at its mass properties, suddenly we're over the limit. So that probably explains why people don't make that many putters out of aluminium, because it's so hard to get to the limit with it. Maybe steel is what I should choose for this. And since it's a fantasy and I don't actually have to machine this, I'm going to say, okay, I'm changing my mind. It's going to be made out of steel. But this is not in any way a viable putter at this point, because we don't have a viable club face yet. So you can't have a vertical face on a golf club. Well, you can, but when people hit the ball, they tend to hit it slightly downwards with the club. And so, because we want it to actually be roughly flat with the putter, we have to put a 4-degree or so upward tilt on this thing. We have to put slightly more on it because it's going to be the shaft's going to be back here, which means the player's going to lean it forwards a bit more. So we'll probably put a 5-degree lean onto this, which I can do by messing around with a couple of features, I think. In fact, let's not mess with that one at all yet. Let's roll back to there. Do a sketch on this face. 1, 2, 3, 4. Between you guys of 5 degrees, and then exit sketch, features, extruded cut, rule. Then if we forward, we're going to find we've lost geometry. So let's actually wrong. Defining the axis is not valid, of course. Right, okay. Yeah, so I deleted the line that I was using as the midpoint uh, for that revolve, and also to feature axis of revolution is that. So that's now happy enough. Cool. Should be sorted now. Yep. And roll forward. That's because that sketch is now messed up. This is the game of spot the grey bits. What's that? I want this to always be ascending. That's the one of the things I want with it. Right. And then turn that back on. So we've got our shape now, and then if we go forward, we've now got a shape with an angle on the face, curved bottom, weird bit in the middle. Let's see where we are with the MOI. that. So we are now like literally on the limit, which is quite cool. And our center of mass feature is way forwards the of our target, which was to have it in the origin. So we can mess around with that by messing around with these sketch constraints. Put more weight in the back part and less weight in the front part. We don't want to make those too horizontal, actually. You see, we've moved that center of mass feature a bit closer. Let's yeah, so it's 6 millimeters forward of where we want it to be. Really moved it as much as I was hoping. Anyway, this is part of the game where you start to think about you have to get the weight where you want it to be, and this is the trial and error part of the game, which is unfortunately going to take a few bit of a while. Let me just fillet these in the way that I was going to anyway, actually. Helps a little bit, but not very much. What's going on there? But it's usually not that obscured. I will say this: it's a lot harder to do a mallet putter than a blade, because with the more space to play with, you get more. It's harder to pick your. It's a lot harder to manipulate where the centre of mass is. Also, like, I'm usually doing a four-way symmetric putter head, so I just design a quarter of it mirror mirror, and it will be in the middle because that's how centres of mass work when you've got four corners that are exactly the same. All right, what I'm going to do is, because we're 5 millimeters out, I'm just going to do what probably the obvious thing to do would have been 5 minutes ago, and just shift the whole thing to be so now this center of mass point is at 0, 0, 0. So okay, so that's the obvious thing to do that I probably should have thought of 4 or 5 minutes ago, or I thought of, but I should have just done 4 or 5 minutes ago. Okay, let's roll back that and get back to our filleting work, which is always an exciting part of the process. Well, got to get your fun where it's available. No, it doesn't really want to fillet that. Okay, and then yes, okay, fine. So that's now it's not going to stab anyone too badly part that we can probably actually manufacture. Let's see where our centre of mass has got to. Is a little bit off, but I'm going to show you how I'm planning to deal with that. So James wants to know if there's a way to verify that the curved shape behind the head is going to have the effect I want, or if that's trial and error. There are mathematical techniques to do it. I'm not going to use any of them today. So the answer is yes, it can be done, and no, I haven't done it here. What I'm looking for with this, the reason I want to curve here is because I'm trying to impedance match for the sound wave. So I think this will be gradual enough to do the job up to at least this point. This pinch point may be too harsh. it's got to reflect off here and here, which would not be what I'd actually want in a putter. So, this isn't necessarily, well, this isn't a very good example of exactly what I would want to do, but it is, as a demonstration of how I would do things in SolidWorks for this. It's not totally misleading, but yeah, I would want to do proper simulations. Oh, and I want to correct something that I said. Well, not correct. I thought a bit more about the what I said in the previous video on acoustic coupling, and um, I think we don't actually need to measure what the golf ball does, because I think we know how long the ball's going to be, or we can put a minimum on how long the ball must be in contact with the putter, which is related to the speed of sound in the golf ball, because the contact time has to last at least as long until the front end of the golf ball knows it needs to get out of the way, and that's how long it takes the impact to travel through the golf ball, and that is going to be more important for the contact time than how fast you're swinging the club, unless you're managing to swing the club faster than the speed of sound in the golf ball, which is going to be, several thousand kilometers a second. Well, probably only one or two, but yeah. So not going to happen unless you've got rocket-assisted golf clubs, which do exist. Right. Anyway, I will put another sketch in here. I'm just going to put in how we attach the shaft to the to the head, because that's going to affect the center of mass. And I'll turn on my axis again for this. So there's a couple of ways you could do this. I'm just going to do it with line. You linear will take you. I'm going to assume that we'll put a 15mm shaft in, which is what I think probably would make the I need to turn on. Going to cut a hole for the shaft and check I didn't go through the bottom, which I didn't, although I did go through all of make a big mess of the middle of my putter there, because what I'm going to do is, instead of making the thing bigger, I'm just going to change this dimension to use a 10mm overall shaft diameter, and then have it recalculate. So that's actually not too bad as a attachment point, although it does go a bit too far. That's the actual putter shafts are about 9mm, a bit under. So let's go with that. There we go. So now that looks tolerable. And if we look down the line, we've got pretty much the centre of mass in the centre of that hole, which is what we were originally after. Now, a lot easier to see. Now, the way I'm thinking of, I would need to machine this because I've got detail on all surfaces now. So it's got to be done in at least 2 fixtures because you can't levitate the object for work holding becomes a problem. And also we've got an issue of reality that so we're now well underneath our target for moment of inertia, which is a little bit bad, but we also need to acknowledge that we can't perfectly machine anything. So supposing that this centre of mass is exactly where we need it to be, which it actually isn't, but supposing even that it were, we can't physically create from steel something that is exactly this geometry. Just humans don't have that kind of technology. So we need to cope with that somehow. And we also need a way, as I say, to hold this in place while it's being machined. So what I'm thinking I'll do is have this lower surface and this bottom edge perhaps done from just a block of steel, and then I'll design something in on this side that lets me attach it to something else so it can be held from this side, and then we can do all the other 5-ish sides, so front, front, left, right, back, top, featuring from that fixture point, because that will mean that all of those 5 should be correct in relation to each other. They might be mildly incorrect in relation to the bottom surface, but no one's going to know. Whereas if we try and, what we don't want is we wouldn't want, for example, that face and this part to be machined in separate operations, because this is marking our center point of the club face, and so we need to be very certain that those line up. And I'm going to attempt to deal with both problems by putting screw holes in the bottom of from the bottom of the club face. So what that will mean is we can put different weights or lengths of screw that weigh different amounts into those screw holes in order to manipulate the center of mass in a relatively subtle way to correct for any machining errors so that it does remain balanced around that point. And also, if we wanted to, we can build a fixture block that screws into the same holes to hold the piece for the second machining operation. So let me just grab a plane and work on that. And then, I mean, this is going to be relatively familiar to anyone who's drawn screw holes before, but I realise that might not be everyone. We try and right. I'm going to use M5 screws for not much better reason than I've memorised their whole dimensions pretty much. It says, and then can't remember exactly. Those ones will work, but I need to make a bigger curvature, a space to put a screw hole in these front wings. So just constrain these. We'll do the magic. Wow, do one of my favourite CAD tricks, or at least attempt it, which is you do things in what is obviously the wrong order. Oh, 2 mils from the surface, and there are better ways of doing what I'm about to do, but currently too lazy to do them. So what we've got there is we can see our problem that the head clearance hole for the head of the screw on the these wings would be cutting through the thing. But let's continue our mission of doing things in the wrong order. And on these holes. Is that the right thing? No, it's not. There we go. Features. Okay. Sorry, that's what I didn't do. I didn't click tab. Right. Yeah. Pause while I click basically the same things again. And then so there probably is a way to do this multiple at a time, but I haven't remembered how it. Well, haven't bothered to learn it yet. Um, and I was wondering if I could do. I certainly could have done the holes before I mirrored it, but I don't think I could do the threads before I mirrored it because I think that I would then end up with left-hand threads on the mirrored side, which I don't want. I haven't though tried that, and it might be fun to test, perhaps on another day. It doesn't actually take that long, as you can see, to do the 4 threads manually. So yeah, the idea is we'll put screws in there to rebalance it if we need to after manufacturing, and we can use those holes as locators for a fixture block for an operation, and we can use those threads to secure the workpiece for an operation. And we specifically want the pattern to only work one way round, so that we can't put the piece on. I could have designed everything so these were a perfect square, but then there'd be many ways to erroneously machine the thing, when having only one way to fixture it is an advantage, not a disadvantage, in my opinion. Right, let's edit you again. And now we've got real view turned off. I can see what I'm doing. That's going to help dramatically. Right. Maintain the opposite geometry. Let's see. Actually, good news. Those aren't the ones I expected to have. I was expecting the other. I was expecting threads 1 and 4 to have problems because I thought we would have changed the endpoint. Interesting. Right, so now we have a manufacturable thing. The center of mass is still close to the center of the shaft in this version, but if we go to the mass properties, the moment of inertia is a bit lower than we would like. So I will just save that and then flick to an assembly view that I made earlier. So this is just got imported into it, the same model we had before. And if I go to evaluate, again, I need to change this to centimeters, grams, TM3. Okay, so we've got exactly the same numbers that we had before because there's only the putter in here. But if I bring in some other components, so let's bring in a few 10mm screws and arrange them suitably. So what we have now is this. So this is a SolidWorks assembly. This is where I can put more than one thing together and tell SolidWorks how they go together. So if I put that so we can say screw, there we go. We select, I think it might be a fine. Do you know what I'm going to do? Just because I can't. I know how to make screws. I just can't remember right now. So we're going to pretend that that didn't happen, and I'm just gonna do a make those two surfaces coincident, and also um, you two concentric, and then in here hit lock rotation. So now those two are together. It's if I got the screw thing to work properly, that screw would have screwed in the assembly. Would have known that it screws in there, and we could check some various things. But the important thing now that we've got that in there is that screw can affect the that screw is part of the assembly, and it will therefore affect this center of mass compared to if I didn't have it in there. So and it will affect the moment of inertia. So let me just add the other screws that I was intending to add, and then insert components, stainless 10. The reason I'm inserting them as 4 separate components rather than inserting one and then copying it is because I want to change some of them to be 5mm screws, some of them to be 12mm screws, to see to what extent we can move the center of mass around with those features. Centric rotation, yeah. Let's So we've got 5290 on the moment of inertia that matters in the rules. And if we go back to just the putter head, we had 5094. So we can, I'm just showing you that the scheme to put screws in to move the moment of inertia, to increase the moment of inertia back to where it was before we put the holes to put the screws in, roughly speaking, works. And let's go back to the thing. Let's just good. Why can't I have a system? Do that. Oh, it's because I'm still in the sketch. That's why I can't make a coordinate system. That makes sense. There we go. So if I go and ask in evaluate mass properties, I can now ask for coordinate system 1, and we can see that we've got slightly better, like minimally better moment of inertia measured here compared to there, which is a little bit disappointing. I thought the point of making the mallet bigger was to achieve that, but probably ought to test my theory and in fact sort of put a cut line round here to say we're only concerned with the moment of inertia of this piece that we hope is acoustically coupled, and test if that's better. But this stream's gone on a bit longer than I was originally intending to already, so I probably won't do that. Anyway, that's approximately how I design putters in SolidWorks. As I say, I'm a little bit better if it's a fully symmetrical blade putter than with this mallet. This was more challenging than I'd expected, and yeah. So I hope that was enjoyable at least, or useful, or if not, why were you watching it? And I'll see you in episode 36, whatever that turns out to be. Thank you very much for watching.